Okay, let's take a look at 2.3. So for this lesson, we're going to use models to find equivalent expressions for perfect squares. So we're looking at perfect squares, yes, a square, and we're looking at the kind of the model and the algebraic expressions to see how they relate. So Optima has a quilt shop where she has many colorful quilt blocks who want to make their own quilts. She has quilt designs that are made so they can size to fit any bed. She bases her designs on quilt squares that can vary in size, so she called the length of one side of a basic square x. And the area of that basic square has the function a of x equals x squared. In this way, she can customize the designs and make it bigger or smaller squares. If Optima adds 3 inches to each side of the square, what is the area of the square? So remember they're saying, hey, the basic square is this one down here, right? So they're saying, hey, this is x on both sides. And they already told us then the area of that square is x squared. And they're saying they're adding 3. So you can kind of see that, hey, there's 1, 2, 3 things right there. So I usually think about this, hey, this length here is a length of 3, right? Whereas this length here was a length of x. Okay, so I'm just going to call this here 3, which means on this side, right, it is also 3. Okay, so she added 3 to each side. When Optima draws the pattern for the square in problem 1, it looks like this. So we want to find the area then of this larger square. This one that if I outline it, let's say in green, we're looking for the area of this entire thing. Okay, so I want to know an expression for that whole area. Okay, so with that in mind, let's go ahead and figure it out. So we already have the x squared all set up. And we know these little blocks here are going to be a unit 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 little ones. Do you guys see that? Okay, these rectangular lengths, you may remember from 2 lessons ago, have a length of x. So these are all a 1 by x, so they have an area of x. So I could look inside it and I could start counting up. I've got 1x squared. I've got 1, 2, 3, 4, 5, 6 x's, so that's a 6x. And I already said I have 9 little blocks. So one thing for the area could be x squared plus 6x plus 9. Okay, so this is looking at the inside area. If I wanted to think about area as the outside, which it should be equal to, but the outside as the side lengths, this side on the left has 3 plus x, or I could write that as I usually write x first, so x plus 3. On the bottom, same thing. It's the exact same length, so it also is x plus 3. And if I multiply those two sides together, I should get area. So then that is also equivalent to x plus 3 squared. Okay, let's look at the next one. A customer service representatives at Optima shop work with customer orders and write up the orders based on the area of fabric needed for the order. As you can see in problem 1, there are 2 ways that customers can call in and describe the area of the quilt. One way describes the length of the sides of the block, and the other describes the areas as 4 sections of the block, right? So when they say kind of the 4 sections, let's look at it in red. They're talking about, hey, this is a section of 3x. You've got this as a section of x squared. I guess maybe it'd be easier if I just kind of draw some lines there. So as I break it apart, it would be these 4 sections that I then drew in red. Okay, and then you got your 9, another 3x, and your x squared. Okay. For each of the following blocks, draw the diagram of the block and write 2 equivalent equations for the area of the block. All right, so let's draw it. So if we have this, I'll start with the x squared in the lower left like they have up there. Not to say that's the only spot you can put it, and we're just adding 1 on each side. But notice to complete the square, I do have to have a little block there. So this is an x, and that's a 1. So this side length is x plus 1, so is this side length x plus 1. So I could say that this is x plus 1 squared, right? X plus 1 times x plus 1 is x plus 1 squared. If I looked inside, I would have x squared. X plus x is a 2x plus 1. Okay, let's do it again. So I've got my x squared. This time I'm adding 4. So I'm going to have, let me just draw like 1, 2, 3, 4 that I'm adding. And we're going to do the same thing on this side. 1, oh, sorry, my bad. 1, 2, 3, 4. And if you're smart when you draw it, you could actually have these like connect to begin with, and maybe a better way to go about it. Kind of extend it over. Okay, I think I need one more line to make that all even. Okay, I'm going to actually draw those bottom ones again for a second. Give me 1 minute. That's looking a little messy. Okay, so these ones I'm going to just extend it to begin with. So extend out from the x squared, and then I have 1, 2, 3, 4. There we go. That looks a little better. Not perfect, but we do not expect perfection out of you, so you're all set. Okay, so now let's go through and we want to count, right? So on the outside, we could say this is x plus 4, right? And same thing with this side, x plus, and we've got 4 more, so x plus 4 squared. On the inside now, I have 1, 2, 3, 4, 5, 6, 7, 8 x's that are rectangles. In addition, I probably should have started with that square that's x squared. So 8x squared plus 8x. And then we got to count the boxes. Little boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So plus 16. So what patterns do you notice when you relate the diagrams to the two expressions for the area? So as you look at this, I would probably focus on, well, first of all, as you take the expression like x plus 1, right, we're just squaring it, right? So we square it, and then what do we notice about the area? So like when we get the x squared plus the 8x plus the 16, something that I notice is if we just look at, hey, we've got 1, and then we also have a 1 there. We've got 4, and then we've got 16. So if you look at just like this upper right corner, notice the dimensions of those 1 blocks are like that size squared. So we notice the end maybe is that number squared. Okay, whereas if I look at the middle terms, like where do you think that 8 is coming from, right? So the 8's a little bit different, and on that one I'm maybe looking at it and saying to myself, okay, well, hey, I noticed that 8 comes from a set of, I've got a set of 4 over here and a set of 4, right? Or when I've got the 1, I've got a set of 1, and I've got a set of 1. So that's where I get my 2 from. So I notice that it's twice, or 2 times, I'll say 2 times that number. So I notice, hey, the x term is twice that number, and then the end is the square term. That will help us. We're going to come back to that in a minute. Okay, let's go ahead and see. So Optima likes to have her little dog Clementine around the shop. One day the dog got a little hungry and started to chew up the orders. When Optima found the orders, one of them chewed up so bad that there were only partial expressions remaining for the area. Help Optima by completing each of the following expressions. So the area they describe for the perfect square, then write 2 equivalent equations for the area of the square. So let's look at A. For A, if you've got x squared, I've got the x squared, and then I have 4x. But you got to think about, if I want to make this into a larger square, right? I've got to take those x's and they got to be divided evenly on both sides. So half of 4 is I'd have 2 on this side and 2 on that side of those x's, right? Because then all of a sudden I have 1, 2, 3, 4 x's. So how many do I have then? In this little part, what I need to add on, I'm adding 1, 2, 3, 4 blocks. What is that equivalent to? If I go through and I look, I've got x squared. Oh, sorry, now I got to look at the outside. So that's the inside of the model. Let's look at the outside. We have an x plus 2 on this side and an x plus 2 on that side. So this is equivalent to x plus 2 squared. Okay, let's look at B. Same thing. We started with x squared, but now I want to make it into this larger square. Okay, so we're going to break it into like these parts. In this case, I've got 6 x's, but I got to split them evenly. So if I split them evenly, I would have 3 on each side of the x squared. So now you got to ask yourself, okay, well, how many little 1 units did I add on here? And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So therefore, as I look at the outside, I've got x plus 3 and an x plus 3 units. So this is the same as x plus 3 squared. Okay, same thing with c. So I start with my x squared, and I'm making it into a larger square. Okay. Oops, those aren't necessarily even, sorry. And here now we have 8x. So we're going to divide that evenly on both sides. So on both sides, we would put 4. So now I do have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I'm going through and I need to figure out a number to add here. So now, how many 1 units do I have? As you count all of these up, you get a total of 16. So now look at the outside of it. We've got x plus 4, and we've got x plus 4. So this is the same as x plus 4 squared. Okay, on D, one last time. So we're going to have a larger square we're trying to make this into. We started with x squared. I'm just going to kind of extend it. And this time we've got 12. So on each side we're going to have 6. This is a little hard to draw. 1, 2, 3, 4, 5, 6. Yeah. And then maybe I'll just do this one in half. And then 2, 3, 4, 5, 6. Okay, so I do, if we keep labeling these x's, I do have 1, 2, 3, 4, 5, 6. And on the other side, I also have 6 of them, right? So I've got a total of 12 x's. Okay, so now if I look at this, and rather than counting, you may notice, hey, if this is a 6 by 6, I have 6 times 6, which is just 36. All right, so then what I'm going to go ahead and do is around the outside, I got x plus 6, and I got an x plus 6. So this is the same as x plus 6 squared. So if I wanted to generalize this relationship, so if I've got ax squared plus bx plus c is a perfect square, what is the relationship between b and c? How do you use b to find c? Okay, just in words, let's talk about what we did. So to use b to find c, we took b and we halved b. So you half b, and then whatever we get for that number, we actually then times by itself, right? And that's kind of what we got in those, right? We got a 6 by 6, right? On this other one, we had like a 4 by 4, which is 16. This is a 3 by 3, 2 by 2, right? Okay, if I wanted to actually put that into like an equation then, you could say halving b is b divided by 2. And if you want to multiply it by itself, a fancy way to do that is b squared. So that's kind of a formula if you like it. If you like it in words, that works as well. For the record, could you use c then to go back and find b? I want to talk about, just for a minute, not that they asked you this, but what about if you have c, how do you find b? If you have c, how do you find b? So in that case, you could say, well, I can just keep guessing. I could guess a number, I could divide it by 2, and I could square it and see if it's bigger or larger than that c value I have. Or another way to think about it would be, okay, if I want to undo this, if I've got c equals b divided by 2 squared, how do you undo a square? You take the square root. So you'd say, hey, the square root of c equals b divided by 2. Then to find b, we're going to multiply both sides by 2. So b equals 2 times the square root of c. So you double whatever you got as your squared root. Okay, that will help you with the bulk of the lesson. A lot of what you're doing here is kind of rewriting, find that missing number, writing it as that perfect square, relating those to the diagram and kind of the area on the outside and the inside of the area model. As for our ready and go, the ready section is reviewing some stuff that you learned last year and a little bit in 8th grade too. They want you to find the x and the y-intercept for this linear equation. So let's think about the x-intercept for a minute. Whenever you're along this x-axis, whether I'm right here at this point, this ordered pair is -6, 0. Whether I'm right here at -2, 0. This is 2, 0, right? This is 5, 0. All of those points you'll notice have something in common. You let y equal 0. And we're going to solve for x. So that's always true. Your x-intercept, y, will always be 0. So we would have 4x minus 3 times 0 equals 12. 3 times 0 is just 0, so I don't even need to rewrite that. I just have 4x equals 12. Divide both sides by 4, x equals 3. Just for practice here, let's write that as an ordered pair. So that is 3, 0. Is our x-intercept. Now let's think about the y-intercept. All along your y-axis, in this case, x always equals 0. So let x equal 0, and then we're going to solve for y. So here we'd have 4 times 0 minus 3y equals 12. 4 times 0 is 0. I'm going to ignore that. I still do need the negative with the 3, though. Divide both sides by -3. Y equals a -4. Let's write that as a point. So x is 0 and the y is -4. If I asked you to graph it, while you could solve that equation for y equals and have it in like your mx plus b form, you have 2 points. And if you have 2 points, there's got to only be one line through it. So I would just plot your x-intercept and your y-intercept. All you have to do now is connect those 2 points and you've got your graph. Okay, I put this table down here just to remind you some of what you're going to end the homework with is writing equations for our linear, exponential, or quadratic. And so I put that there as a reminder for you, but I think we've practiced that enough in our last unit that you don't need any review